the graphs of rational functions. A rational function is a quotient of two polynomial functions. That means that we divide them. The parent rational function is f of x equals 1 over x. An asymptote is a line that a function approaches but never touches. The definition of a vertical asymptote: the line x equals a is a vertical asymptote for the function f of x if f of x approaches infinity or f of x approaches negative infinity as x approaches a from either the left or the right. So it's a vertical line indicating where the function goes to positive or negative infinity as x approaches some value. So as a function, it's going to look like this, where you've got this function that gets closer and closer to, let's say, 3. And so this gets closer and closer and closer to 3, but never touches it. It just keeps going down and down and down. When you're asked to write the vertical asymptote, it should be the equation of a line. So this vertical asymptote would be the line x equals 3. Vertical asymptotes occur when the denominator of a rational function is 0, because we can't divide by 0. Wholes occur when a factor is present in both the numerator and the denominator of a rational function. For example, x squared minus 1 over x minus 1. Right? If we factor this, x squared minus 1 factors into x plus 1 times x minus 1. And the x minus 1's cancel out, and we just have the graph of a line x plus 1. But because we didn't graph x plus 1, we graphed x squared minus 1 over x minus 1, we have a hole at x equals 1. Because we still can't divide by 0, even though we canceled it out. So be careful. Holes can look like vertical asymptotes if you're not paying attention, because vertical asymptotes also occur where the denominator is 0. But when vertical asymptotes, you don't have the factor that cancels out. With holes, you do. So always make sure to factor the numerator and see if anything cancels out before you start looking for your vertical asymptotes. Horizontal asymptotes. The line y equals b is a horizontal asymptote for a function f of x if f of x approaches b as x approaches infinity or as x approaches negative infinity. It's a horizontal line that the function approaches as x approaches plus or minus infinity. So if I've got a function that looks like this, I have a horizontal asymptote at 0. Right? Because as x goes to infinity, my y value is getting closer and closer and closer to 0, but never touching it. Same thing at negative infinity. It's getting closer and closer and closer to 0, but never touching. And we write that as the equation for a horizontal line, y equals whatever the value is. In this case, y equals 0. You have to write your asymptotes as equations of lines. Y equals whatever or x equals whatever. I will definitely take points off for that on your test. Watch, half of you do it anyways. The location of a horizontal asymptote depends on the degree of the numerator and the denominator. We talked about degrees last week. The degree of a polynomial is the power of its largest exponent. If the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. So, x cubed plus 2 over x plus 1. The numerator has a degree of 3. The denominator has a degree of 1. If there's no power shown, it's a degree of 1. Degree of the numerator is bigger than the degree of the denominator, no horizontal asymptote. You can see this is a very weird looking graph. It does have a vertical asymptote at -1, but it doesn't have a horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is at 0. So this has a degree of 1. This has a degree of 2. The degree of the numerator is less than the degree of the denominator, so the asymptote is at 0. And so here you can see that this function approaches 0 and never touches it. Last one is the tricky one. If the degree of the numerator equals the degree of the denominator, the horizontal asymptote is the ratio of the leading coefficients. So this has a degree of 1, and this has a degree of 1. So the ratio of the leading coefficients means whatever fraction you get when you divide 2 by 1, which in this case is 2. So your horizontal asymptote is at y equals 2 over 1, which is y equals 2. And so on this graph, you've got this horizontal line at y equals 2 that the function approaches but never touches. Find the asymptotes for the function f of x equals 3x minus 1 over x minus 2. The numerator has a degree 1. All right, this is a 1. The denominator is also a degree 1. So your horizontal asymptote is the line 3 over 1, which is this line y equals 3. The numerator doesn't factor, nothing cancels out, so you don't have any holes. So your vertical asymptote is where the denominator equals 0. Your vertical asymptote is the line x equals 2. Graph the following function using transformations of the parent function f of x equals 1 over x. So the parent function goes through this point 1, 1 and has a vertical asymptote at 0 and a horizontal asymptote at 0. Also goes through the point -1, -1 and has those asymptotes from the bottom. So this is the parent function, f of x equals 1 over x. Now we use our transformation rules. If we have something inside the function, so this is g of x equals f of x plus 5, we add or subtract something inside the function, that shifts it to the left or the right. In this case, that's going to shift it to the left by 5. Which means we're going to have asymptotes. Our asymptote that was at 0 is now going to be at 5. Our horizontal asymptote doesn't change because the function doesn't shift up or down. We just shifted it to the left. So this is g of x equals 1 over x plus 5. Here we have h of x. We have a negative out front, and we multiplied the function by 2 inside, which is going to horizontally shrink the function. So what happens is that it ends up being closer to the axis here, and actually it's not that because it's also upside down because of that negative out front. So it's going to, instead of going through the point here at 1, 1, it's going to be 1/2 -1. And it's going to go like this, reflected over the x-axis. And then you're also going to have this. That's h of x equals -1/2x. Our transformation here, we multiply by 4, so that's a vertical stretch by 4, and shift it to the right 3. So our asymptote now is at 3, and this point is instead going to be up here. The point that would be 1, 1 over from the asymptote is now up 4. So this is still going to go to infinity, it's just thicker right here. 1, 2, 3, 4. So still go to infinity here, and still go to infinity there. That's k of x equals 4 over x minus 3. And then our last one, vertical stretch by 6. We're reflected over the x-axis, and we're shifted 2 to the right. So our asymptote is 2 to the right. We're going to be upside down, and we're going to be stretched by 6. So like that. And then 1, 2, 3, 4, 5, 6. So that's going to approach the asymptote, and that's going to approach infinity. Approach 0 as it approaches infinity. So this would be m of x equals -6 over x plus 2. So all the same transformation rules that we learned apply to f of x equals 1 over x as well. Number 3. The creation of standard chemical solutions requires precise measurements and appropriate mixing. For example, a chemist may have 50 liters of a 10 molar sodium chloride solution. The solution must be diluted so it can be used in an experiment. Adding 4 molar sodium chloride solution to the 10 molar solution will decrease the concentration. The concentration C of the mixture can be modeled by the equation C of x equals 500 plus 4x over 500 plus x, where x is the number of liters of 4 molar solution added. We want to first write the function as a transformation of the parent function f of x. And in order to do that, we're going to need to divide these functions. So we're going to do long division, and we're going to divide 500 plus 4x over 500 plus x. And actually, I'm going to switch this around, and I'm going to write this as 4x plus 500 over x plus 500, just for the ease of my multiplication. So 4x plus 500 over x plus 500. So x goes into 4x 4 times. That's going to be 4x. 4 times 500 is 2,000. Switch the signs. 4x's cancel out. This is minus 1,500. So x doesn't go into 1,500, so that's our remainder. And we can write that remainder as just 1,500 over x plus 500. So we're going to get the function c of x is equal to 4 minus 1,500 over x plus 500. Or again, to write this in a more standard way, negative 1500 over x plus 500 plus 4. So what transformations are occurring here? This is going to be shifted up 4. Having this in the denominator means that this is shifted to the right 500. Sorry, left. That's a plus. To the left by 500. We have a negative, so that reflects it over the x-axis. And we have a vertical stretch by a factor of 1500. So if we were to graph this function, let's say that our scale here, this is just going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. But this is going to be 100, 200, 300, 400, 500, and so on. And so we are shifted our point that would be at 0, 0 in the function 1 over x is going to be shifted 4 units up and 500 to the left. And that is where our asymptote, so we would have our vertical asymptote that would go through, that would be the line x equals 0, is now x equals negative 500. And the horizontal asymptote that would be y equals 0 is now y equals 4. And we are going to reflect it over the x-axis, so it's going to look like this and flatten out. And then it would also be this way, but it doesn't make sense for us to have a negative amount of solution, right? X is the moles of solution that we add to the existing solution, and you can't add negative amounts of a solution. So really this part over here doesn't mean anything. Neither does this part really. So the function looks approximately like this. I'm not going to get into exactly how much the stretch does things. But the function looks approximately like this. So your asymptotes, we have a horizontal asymptote at y equals 4 and a vertical asymptote at x equals negative 500. So the horizontal asymptote is going to be the concentration of the solution that the concentration approaches as we add more and more of this 4 molar solution. So as the amount of solution added gets infinitely large, the concentration of the solution approaches 4. The horizontal asymptote is going to be a point where we cannot add any of the solution. So as we have less and less of the solution added, the concentration of the solution becomes negative, which doesn't make sense in terms of a real life problem. This is theoretical. It wouldn't make any sense because we can't add negative amounts of solution. We can't have a negative concentration. Slant and oblique asymptotes, same thing. Third type of asymptote is a slant asymptote, also called an oblique asymptote. Slant asymptotes occur when the degree of the numerator of a rational function is exactly 1 greater than that of the denominator. So for example, this has a degree of 3, and the denominator has a degree of 2. So the formal definition, the oblique line L is a slant asymptote for a function if the graph of f of x approaches L as x approaches infinity or x approaches negative infinity. What that looks like on the graph is something like this, where you've got some line here, and this looks like it's approaching that line. It looks like it's like that part of the function becomes linear, although it doesn't actually approach the line. To find the equation in the slant asymptote, divide the numerator by the denominator. We do this using long division. So this is going to be x cubed, and I'm going to write this as 0x squared plus 0x plus 1, just to make sure that I don't lose anything. The zeros are placeholders here, and I highly recommend that you write those placeholder zeros. X squared goes into x cubed x times. That's what you have to multiply by. So x times x squared is x cubed. Subtract that. That's going to be 0. X squared goes into 0 times. So that's 0x squared is 0. X squared goes into x 0 times. That's going to be 0x. And then the plus 1, x squared doesn't go into 1, so your remainder would be 1 over x squared. But when we are finding the slant asymptote, we disregard the remainder. So here your slant asymptote is just the line y equals x. Just like with horizontal and vertical asymptotes, always write your slant asymptote as the equation of a line. Y equals something. And yeah, here's the line, right? If we graph the line y equals x, we can see that the function gets closer and closer to that line as x approaches infinity. So we would write that using our notation for end behavior as x approaches infinity, f of x approaches x. One more. Determine the slant asymptote for f of x equals 2x squared minus 3x plus 1 over x minus 2. So 2x squared minus 3x plus 1 over x minus 2. What do we have to multiply x by to get 2x squared? We would have to multiply it by 2x. So 2x times x would be 2x squared. 2x times negative 2 would be negative 4x. Switch all your signs. That cancels out. Negative 3x plus 4x is going to be x. Bring down your 1. What do you have to multiply x by to get x? That's just 1. Distribute that. That's going to be x minus 2. Switch your signs. X's cancel out. That's going to be 3. Your remainder is 3 because x does not go into 3, but we don't care about the remainder. Our slant asymptote is the line y equals 2x plus 1. All right, and so here's the line y equals 2x plus 1, and this would be what the graph would look like. All right, so using what we know about functions, graph y equals x plus 3, x plus 1 over x times x plus 3 times x minus 2. So we know that this, the numerator has a degree 2, so we got 2 x's. The denominator has a degree 3. So degree of the numerator is less than the degree of the denominator. There's a horizontal asymptote at y equals 0. We have a whole at x equals -3, because that would cancel out. If we plug -3 back into the function after we cancel this out, that's going to be -2, and that's going to be -3 times -5 is positive 15. So we have a whole at -3 2/15, -2/15. We're going to have vertical asymptotes at x equals 0 and x equals 2, where the denominator equals 0. So here equals 0, or x minus 2 equals 0, which is x equals 2. So horizontal asymptotes. We do not have a slant asymptote here. If we have a horizontal asymptote, we can't have a slant asymptote. We're going to have a vertical asymptote at 0 and a vertical asymptote at 2. We know at -3 the function is negative. So at -3 we've got a hole like right there. So the function is going to approach the asymptote here and is going to approach the asymptote down here. If we pick a number like 1 and we plug this into the function, 1 plus 3 times 1 plus 1 over 1 times 1 plus 3 times 1 minus 2, that's going to be, that'll cancel out, 2 over -1, so that's -2 here. So the function's going to be negative. We know the function does go through 0 at -1. This is the weird one where it's, I think it's actually, we know the function, I think that it actually does this. I think it actually goes through 0 and then the asymptote goes that way. Because where we set the numerator equal to 0, that is going to be your 0 or your x-intercept. That's the only place where it goes through 0, so anything that stays negative has got to stay negative. And if we pick like 3 and we plug it in here, we're going to get a positive value. So this has got to be positive here. And thank goodness that is the end of this chapter. Study for your test on Wednesday.